Our first lecturer this afternoon is David Mateus, who will continue to tell us about string theory and ring.
Thank you. So yesterday we saw how to model fundamental matter as D-brane probes, and we discussed mesons and their spectrum. And what I'd like to do today is to start making contact with the experiment. And that is the reason why we will consider finite temperature, and that will lead to a connection to Rig physics. So I'm going to start without quarks, and then after that we'll add them in and see how they change the story. So the motivation for introducing finite temperature is as follows. N equals 4 super Young-Mills and QCD at 0 temperature are very, very different theories. QCD has a dynamically generated scale, so it's not a conformal theory, and it's not supersymmetric. N equals 4 is both conformal and very supersymmetric, so they are very different theories. However, QCD at some temperature TD confinement, which is around 175 MeVs, undergoes a crossover. This would be a phase transition, a first-order phase transition at large n, but in QCD with n equals 3 and the values of the quark masses that are given to us in nature. This is a rapid crossover. But the point is that you go from a confinement phase to a deconfined phase. This phase is referred to as the quark-gluon plasma, because the main property of this phase is that quarks and gluons become deconfined. And so they look like a plasma. So by analogy with electromagnetic plasmas, this is referred to as the quark-gluon plasma. And so the idea here is that perhaps, this is for QCD, one can use n equals 4. That's the hope. N equals 4 theory, which is a non-confining theory. At finite temperature, all supersymmetries are broken. Temperature breaks all the supersymmetries. So at finite temperature, n equals 4 looks like a plasma of quarks, sorry, not quarks, but gluons and matter in the adjoint representation. But the idea is that perhaps this is a good model to study the properties of the quark-gluon plasma. And what we're going to do is to try to explore that possibility and see where it leads, and then judge a posteriori. OK? That's the motivation. You will see that this is particularly important, not so much for thermodynamics, because after all, the thermodynamics of QCD can be very well studied on the lattice. The lattice is a fantastic tool to study the thermodynamics. But as soon as you go to more dynamical observables, for example, hydrodynamic transport coefficients, such as viscosities, etc., then the lattice, because of its Euclidean inherent formulation, is not particularly well suited for those, even though there's been progress. And I don't know if we'll hear about that in the lectures this week. But in any case, at the moment, it's very hard to study certain dynamical observables, which require Lorentzian signature physics, real-time physics, with a Euclidean formulation on the lattice. Good. So how are we going to do this? Well, we need to use the ADS-CFT correspondence between n equals 4 super Young-Mills and type 2b string theory, but at finite temperature. So how do we do that? Well, adding temperature means that you're adding energy to the theory, to the system, but no charge, no D3 brane charge. And so this suggests that what you should do is take a decoupling limit for non-extremal D3 branes, for black D3 branes. And so the metric, in that case, takes the following form. It's just a little modification with respect to the metric I wrote down yesterday. Actually, I want to write down this explicitly. Well, this is good enough. OK, where f is the new function that appears in this metric, which is given by 1 minus some parameter r naught to the fourth divided by r to the fourth. This is the result of taking a decoupling limit for a metric for NC extremal D3 branes. And the only new parameter is this R naught, which is related. It's going to be related, as we will see in a second, to the temperature. Okay, so if you set the temperature to 0, R naught will be 0, and then this reduces to the previous ADS5 crosses 5 metric. So the first thing you notice is that for little r much larger than R naught, f is essentially 1, and this metric reduces to the metric we studied yesterday. And that's exactly what you would expect, because as we'll see, R naught is proportional to the temperature. So if you go to energies, or very high energies, which means very large radial positions towards the boundary, then the temperature should be irrelevant, because the energy scale that you're looking at is so much larger than the temperature. In other words, the temperature doesn't change the UV physics. However, the main difference between this metric and the one we looked at yesterday is that at r equals R naught, there is a finite area horizon here. With a temperature, with a Hawking temperature, which we will identify with the temperature in the gauge theory. Now, the simplest way to compute this temperature, yes?
X is not compactified.
Sorry?
X is not compactified, is it?
No, X is not compactified. This X here represents X1, X2, and X3, and they are all non-compact.
So it's not finite area.
It's not what?
It's infinite area.
It's infinite area. Well, yes, it's a finite. Thank you. It's, you can always trust that there will be a relativist in the audience. It's finite area density. So, thank you. I'll come back to this. So this is this horizon is a translationally invariant horizon along the x directions. If you factor out the volume of these x directions, you get a finite area density per unit volume in the x directions. That's what I meant. Thank you. Good. So the easiest way to compute this temperature is to take this metric and perform a Euclidean continuation in which you send t to I t Euclidean. That means that the time direction, and then you identify you periodically identify t Euclidean with period beta, where beta is 1 over the temperature. And this beta is selected by the fact that once you periodically identify the Euclidean time, you see that in this metric, f goes to 0 at r equals r naught, and that means that this circle shrinks to 0 size. And you're instructed to choose beta, this period, in such a way that the geometry is regular at r equals r naught. And the physical interpretation of why you identify periodically the time direction, the Euclidean time direction, is that you want to compute a partition function of this form. And one way to implement this trace is to periodically identify the Euclidean time direction. So if you do this, this is a little exercise. You find that beta is pi r squared over r naught. And remember, this is 1 over t. So you see that t is proportional to r naught. And that's why setting r naught to 0 means that you're back to the 0 temperature duality that we studied yesterday. Any questions so far? Thank you.
Finite, of course, you meant non-zero.
Yes. Thank you. Yeah, when I say finite, I mean non-zero and not infinite. So the first calculation that I'm not going to do, that's a very, very simple exercise, and I think you have actually seen it before in some of the lectures, is to use this metric to calculate the entropy density of n equals 4 super young meals at finite temperature and strong coupling. The supergravity description is good at large n and strong coupling. And so what we are going to do is to identify the geometric entropy of this solution, the Bekenstein-Hawking entropy, which is the area divided by 4 times Newton's constant. We will interpret that as the entropy in the gauge theory, as you would expect. So I'm not going to do the calculation, but you see it's very easy. This is a horizon that's translationally invariant in these directions. So this entropy is proportional to the 3 volume, which is infinite in those directions. That's the only infinite factor. Okay, so this V3 is just integral d3x. But the entropy density is finite. And if you compute that, what you get is pi squared over 2 and c squared t cubed. So let's look at this formula for a second and interpret it. First of all, the nc squared factor follows from large n counting, and it's what you would expect because of the fact that the number of degrees of freedom in a deconfined phase in a theory with fields in the adjoint representation, like the gluons of SUNC, has nc squared degrees of freedom. So that's the scaling you expect. The factor of t cubed has to be there by dimensional analysis, because in n equals 4 super young meals, the only scale, once you introduce the temperature, is the temperature itself. And the entropy density has dimensions of energy cube. And so this factor is also expected. But what's remarkable, first of all, is that this formula shows that the entropy density of n equals 4 super young meals at infinite coupling, in the limit of very large coupling, is finite. Okay, there's no dependence on the coupling here. In particular, this is a finite result. And even more remarkably, this entropy, this Bekenstein-Hawking entropy, is equal to the entropy. Remember, this is what we calculate at lambda going to infinity, very strong tooth coupling. This is equal to the entropy of a free gas of n equals 4 particles, namely at lambda equals 0, up to a factor of 3/4. Are there any questions so far? Yes?
Hi, can I just check what the subscripts are on those 2 letter T's you have at the bottom of both of these?
Here? Yeah, Hawking and gauge theory.
Perfect, thanks.
Any other questions? Yes?
Where does this 3/4, where does this last equation come from?
Yeah, what I'm saying is that if you calculate the entropy density of a free gas, no interactions, of n equals 4 particles, where you have a given number of bosons and a given number of fermions, you get a number, you get a result that of course scales like nc squared t cubed, but the coefficient is related to this coefficient by this factor of 3/4. In other words, from going to 0 coupling to infinite coupling, the entropy density only changes by a factor of 3/4. It gets reduced by a factor of 3/4. Any other questions? Okay, so this is one example of how to use holography to compute thermodynamic quantities, in particular the entropy density of the gauge theory at strong coupling. The next thing I want to show you how to do is how to use holography to compute transport coefficients. Okay, so let's talk about a little bit about hydrodynamics then. In particular, we're going to focus on the shear viscosity. So what is hydrodynamics? Thermodynamics is the description of a system in perfect thermal equilibrium. Instead, hydrodynamics is a low energy effective description of the system, of fluctuations in the system around thermal equilibrium at arbitrarily long wavelengths and with small amplitudes. So it's an effective description of the low energy fluctuations around perfect thermal equilibrium. And just like any other effective theory, it is characterized by some coefficients, in particular some transport coefficients, such as the shear viscosity that I'll describe in a second, that you should be able to calculate with a microscopic theory. Okay, so in QCD, for example, if you could really calculate in any regime, you should be able to calculate the shear viscosity of that quark gluon plasma above the deconfinement temperature using the fundamental microscopic QCD Lagrangian. So what is this shear viscosity? This is just an example of a transport coefficient. In particular, it's a diffusion constant for the transport of momentum. So imagine that you have some distribution of momentum in a fluid, say in the y direction, in such a way that it's not homogeneous everywhere, but there is a gradient in a given direction x. Then, just like any conserved charge, you expect that this momentum will diffuse to compensate for this difference at different points. Now, in the linear response approximation, you know that the momentum flow of y momentum in the x direction, which is measured by the xy component of the energy momentum tensor, is going to be proportional to the gradient in that direction of the momentum density in the y direction, which is T0y. And the constant of proportionality here is a diffusion constant that's called the shear viscosity. So the shear viscosity measures how effectively momentum in a given direction is diffused in an orthogonal direction. And this relation I wrote down here is called a constituent relation, because it tells you what the flow is given the gradient of the conserved charge. Any questions about this? Good. So one word of caution, in case you have any intuition about what the shear viscosity is that the shear viscosity of weakly coupled systems, for example, an almost free or weakly interacting gas, is very large, not very small. So I don't know if your intuition about what the viscosity of a gas should be, like air, but it's actually very large, not very small. And the reason for that is that if you have a system that's very weakly interacting, then a particle moving up here with a characteristic momentum py, which is large, can travel for a long distance. The mean free path is very long because this is a weakly interacting system, before interacting and therefore equilibrating again with other particles. So the transport of momentum is very efficient. Okay, because a particle can travel a long distance, therefore moving between layers with very different momenta, and thereby transferring momenta very efficiently. So at weak coupling, eta is large. And we'll see what happens at strong coupling. And we will also confirm this in a second. Now, in quantum field theory, if somebody gives you a microscopic quantum field theory, you can...
Large compared to what are the dimensions?
Let me get to that. I'll write down a sensible formula. Or if you like, I can give it to you now. So eta normalized to the entropy density, because that's a measure of the number of degrees of freedom in the system. So it's a more meaningful measure of how viscous your system is. That's dimensionless, so that's much larger than 1. So in a quantum field theory, if you are given the microscopic Lagrangian, not surprisingly, you can actually calculate what the viscosity is by computing a 2-point function. So can everybody see if I write here? Yeah? OK, so in quantum field theory, the viscosity is given by a so-called Kubo-like formula, which says that eta is given by the limit of frequency going to 0 of -1 over the frequency times the imaginary part of a 2-point function, a retarded correlator, xy, xy, of omega at 0 spatial momentum, where this correlator, g retarded mu nu lambda rho of omega and q, this is just the Fourier transform d for x t to the minus I q x theta of t, and here you have a commutator of t mu nu at x with t lambda rho at 0. So let me make a few comments to make this formula plausible. First of all, we are setting the spatial momentum to 0 and taking a 0 frequency limit. The reason for this is that hydrodynamics applies, as I said, at low energies and long wavelengths. So this Fourier transform at 0 momentum and low frequency is precisely reflecting that fact. Moreover, the imaginary part here is associated to the fact that, that we are looking at a diffusion process. And finally, this correlator here, this commutator here, measures, as you would expect, for a diffusion constant. You would expect that to be related to this commutator, because this measures how a perturbation that you create at the point x equals 0 propagates to the point x. So once somebody hands you this formula, all you need is to be able to calculate a 2-point function of 2 stress energy tensors, plug it in this formula, and then take this limit, and that gives you the shear viscosity. We don't know how to do that in QCD, but we're going to do it, or I'll sketch how you would do that for n equals 4 super Young-Mills, and I'll tell you what the result is. And that, together with the entropy density, is going to allow us to make contact with physics at RIC. Any questions so far? Yes.
Why concentrate on the shear velocity and
Shear viscosity.
shear viscosity, for example, not longitudinal viscosity, or for example?
Right. So
Simply this.
there are 2 reasons for that. The first one is that when people try to understand the experimental data at RIC, they run hydrodynamic simulations, and one of the crucial parameters is this ratio of eta over s. So everything is very sensitive to that specific combination. Other transport coefficients are important too, but that one seems to be particularly important. That's one reason. And the second one is that, as I will explain, this ratio for eta over s, when you calculate it in n equals 4, gives you some result. And then when you calculate it for other holographic theories, they always give the same result too. So it's a universal ratio, at least for, as far as we know, for gauge theories with a gravity dual. That's not true for other transport coefficients. And so because here we're not calculating in QCD, the only hope that you have of being able to extrapolate to something that applies to QCD is for coefficients that are universal. Because if they are model dependent, within this set of theories that have a gravity dual, almost certainly they will not be applicable to an even more different theory like QCD.
Do you know in advance whether it's going to be universal before you do the calculation?
I can tell you whether you should know and whether people knew. People didn't know this.
They should have known.
Well, a posteriori, in hindsight, it's easy to say, and I'll give you an argument for why it is universal. But in principle, in fact, the way this happened is it was calculated for n equals 4. They got some result, and then they did it for the M2 brane and the M5 brane, and they got the same result. And then they started doing it with more complicated holographic theories, and they always got the same result. And then they started thinking, how come that we always get the same result? And then they came up, there are general arguments you can give and the very general assumptions that guarantee that it's going to be universal. But understanding what transport coefficients are going to be universal is part of the challenge in trying to compare to QCD. Sorry, did you have a...
Also, the bulk viscosity is forced to be 0 by conformal invariance.
In this case, yes.
So there's nothing to calculate in this case.
In this case. But you could certainly calculate it in non-conformal theories. Right. And people have done that, and it's not universal. Yes?
Is the universality, is that a large N result? Or?
So I'm running ahead of myself. Let me tell you what the result is, and then I'll discuss all the physics associated to that, to what extent it's universal, and then I'll take questions about that. But let me first say how to calculate it and what the result is. Okay, so how would you go about calculating that correlator? So last week you had a course on ADS-CFT, and presumably somebody told you that there's a prescription for calculating correlators. In particular, two-point functions are very simple, because all you need is a linearized equation of motion of some fluctuation in the gravitational background. So let me sketch that. So we're interested in a two-point function of an operator in the gauge theory, which happens to be the stress energy tensor. So the first thing you need is to know what is the field in the dual string theory description that's associated or that's dual to this operator, and that happens to be the metric itself. Has anybody told you this before? You did, Mukun? Okay. So once you have the dual field, then you know that the two-point function schematically is just given by taking, of course, two functional derivatives of the partition function for either the gauge theory or the string theory with respect to the field to the source dual to T mu nu. Okay, so this is given by let me put it like this, of the effective action evaluated at h equals 0. So what you do is you consider this metric here, then consider a fluctuation h around that metric, expand the supergravity, well, solve for the fluctuation, plug it back into the supergravity action, and take two functional derivatives with respect to that fluctuation, and then evaluate the result at h equals 0. Is this clear? At least what the procedure you would have to follow is? Yes or no? Good. Okay, so the result, you can find this calculation in papers in the literature, but it's a little bit too technical to do it here. But the result you get is very simple. You get that from this correlator, you plug it in this formula, and you get the viscosity. And the result you get is that eta is pi divided by 8 times nc squared t cubed. And this immediately implies that this ratio is 1 over 4 pi. And this is an important result. Remember, the entropy is up there. So this S here is the entropy density. Okay, so I'm factoring out this volume factor. Now, the reason this result is important is because, as I was saying, it happens to be the same for any gauge theory for which we have a gravity dual. There's no counterexample to this. This applies for theories in different numbers of dimensions, with or without a chemical potential, and with or without fundamental matter, as far as we know. There's no counterexample. And that's not true for other transport coefficients or for other ratios. Now, let me give you an argument for why this is so universal. Excuse me?
Yes, effective is for the supergravity.
Yes, that effective action is, in this case, the supergravity, type 2b supergravity action, yeah.
How do you determine whether you get a retarded Green's function or any other Green's function? Formula.
Sorry, what's the question?
I mean, you specifically identified the retarded Green's function over there as the relevant one to define eta. But in the formula at the top, the correlation function of two t's, how do you determine which Green's function you
Good, thank you. So that's part of the prescription for computing correlators in the presence of a horizon. When you have a horizon in your metric, you have to decide the retarded and advanced correlators correspond to solving the field equation for the perturbation with given boundary conditions at the horizon. So the retarded one corresponds to ingoing boundary conditions, and the advanced correlator corresponds to outgoing boundary conditions. So that's the way in the gravity calculation, even though I didn't explicitly say that, you distinguish between the retarded and the advanced one.
So
Yeah.
how does one determine the normalization? That two-point function.
Good. That has to do with the normalization of the one-point function as well. So that's part of, you have to be careful when you write down the prescription. For example, what Newton's constant is. So basically this, I forgot to say, thank you for the question. So I forgot to say, the reason you get an NC squared here is precisely because of normalization, because Newton's constant goes like GS squared, the string coupling squared, which, remember, this is g to the 4th Yang-Mills, because GS is just g squared. And this in the large n goes like 1 over nc squared. And so the supergravity action has a 1 over g Newton in front, which leads to an nc squared factor. The same is true for eta. Yeah, this formula here, because we derived it using supergravity, is only valid in principle at infinite coupling and infinite n.
But a similar calculation for the free theory, of which only the coefficient differs, would not, of course, involve G Newton in any way.
No. That's
And
it.
your
From
explanation is a bit...
I'm giving you the origin of that factor in the gravity description. In the gauge theory description, it's just because you're in a deconfined phase. So the number of degrees of freedom scales like nc squared. Good. So let me give you an argument that shows, at least under quite general assumptions, why this ratio is universal. So what is the here? The reason for that is that both the viscosity and the entropy density are associated and are in fact proportional to the area of the horizon. Of course, the entropy density is given by this formula, so it's as you can see, it's proportional to the area of the horizon. And the viscosity, using that prescription I gave you, you can actually show that it is equal to 1 over 16 pi g Newton times the absorption cross-section for a minimally coupled scalar in that metric. This equality here is something you can prove using this prescription, this formula, and then writing down explicitly and looking at the way, in detail, the way you calculate this two-point function, this correlator, holographically. Okay? You end up looking at a fluctuation of the metric h, but you can rewrite the equation of motion for this fluctuation as the equation of motion for a minimally coupled scalar, and then show that eta is exactly equal to this combination. So up to a factor is equal to the absorption cross-section. And now this is known to be equal to the area, this absorption cross-section, the area of the horizon, at least for static black holes. You can prove a theorem that shows that in the zero frequency limit, the absorption cross-section is equal to the area, as perhaps you would have suspected.
Do you mean minimally coupled or conformally?
Minimally.
Only.
Minimally.
And if you take them conformally coupled?
I don't know. But that's not the equation of motion you get for that fluctuation.
That's a massless scale, right?
Yes, I think, yeah, it's a massless. Thank you. Massless minimally coupled, yeah.
David?
Yes.
Eta over S is presumably the same even when you include chemical potentials for rotation. Right?
No, so this, yeah, so eta over S by explicit calculation, in those cases, for stationary but non-static metrics, you can show that it's still given by 1 over 4 pi. And so I suspect there is a generalized theorem that proves something like that. But as far as I know, nobody has done that.
That's right.
Yeah. So thank you. So this argument I'm giving here doesn't apply to theories with a chemical potential, because chemical potentials are dual, at least chemical potentials for our charge. Those are dual to rotation in ADS 5 crosses 5. So the metric is no longer static but stationary only. And this theorem I'm quoting here that says that this absorption cross-section is equal to the area has not been proven for stationary metrics, only for static metrics. But you can go ahead and do that calculation explicitly and you still get 1 over 4 pi.
If you stick the H bars and C's back into them,
Yeah.
1 over 4 pi,
Yeah.
what happens?
There's an H bar here and a Boltzmann constant here. So there are no C's. And that led some people to suspect that this could be still true for non-relativistic theories or systems. But if you ask well, I'm running ahead again. Let me get to that. Okay, so obviously once you know this, you take the ratio of eta over S, and then the area cancels, Newton constant cancels, and you get 1 over 4 pi. So that's why this ratio is so universal. It's because it is associated to properties, universal properties of black hole horizons. Any more questions about that? Okay, so if there are no more questions, then let me make a few comments about this. The first one is that, as I said, this ratio eta over S equal to 1 over 4 pi is very small. What very small means here is that, for example, for water, which after all gave its name to hydrodynamics, this ratio is 380 times larger than 1 over 4 pi. So for water, eta over S is about 380 times 1 over 4 pi. For liquid helium, this is about 9 times 1 over 4 pi. And for a weakly coupled quantum field theory, if you calculate eta over S at weak coupling, this goes like 1 over lambda squared log lambda. So it's much larger than 1. That's one set of comments. The next one is that, as somebody pointed out, this result here was obtained using supergravity, so it's only valid at very large n and very large lambda, but you can calculate at least the first correction in lambda, away from lambda equals infinity. So for n equals 4, super Young-Mills, eta over s is actually equal to 1 over 4 pi times 1 plus a positive number divided by lambda to the 3/2 plus subleading terms. And so what you see is that going away from lambda equals infinity slightly increases the value of this ratio. And therefore, the simplest possibility, if you plot this ratio as a function of the coupling, is that you know over here it's 1 over 4 pi, and you know this curve goes up, and you also know that at weak coupling it diverges. And so the simplest possibility is that this is a monotonically decreasing function of the coupling that saturates at 1 over 4 pi at infinite coupling. Moreover, so this is concerning 1 over lambda corrections. 1 over n corrections are very, very hard to compute, but you can at least calculate one such correction, which is the one associated to introducing fundamental matter in the theory. Remember, when you introduce fundamental matter, the quarks will give a contribution to this ratio that's suppressed by nf over nc, just like their contribution to any generic quantity in the large n. And so what that means is that the first non-trivial 1 over n correction is actually, and the leading correction is associated to the quarks. Because if you were to calculate the first 1 over n correction for a theory with only adjoint matter, or gluons, that would come at order 1 over nc squared. The expansion in the large n for theories with adjoint matter only is an expansion in 1 over nc squared. If you have quarks, that's an expansion in 1 over nc. And so this is actually the most important leading correction. And to leading order in this correction, in this ratio, you can show that at least for the D3, D7 system that I discussed yesterday, so n equals 4 with fundamental matter, and a large number of other theories with adjoint matter and quarks, the result, eta over s, is not corrected. It's still equal to 1 over 4 pi. So eta and s are both corrected at order nf over nc, but the ratio is not. So all of this suggests that, and led, well, some of this evidence they didn't know, but in any case they conjectured, some authors conjecture that 1 over 4 pi is a universal lower bound at least for any relativistic quantum field theory at finite temperature.
So what about the phenomenon of superfluidity?
Ah, good point. So when people talk about superfluidity, what they mean is that the viscosity goes to 0. But of course, the entropy density goes to 0 too. And what happens is that the ratio is above 1 over 4 pi. Good. Any more questions about this?
Where does the log lambda come from in the interpretive calculus?
Sorry, say again?
In the ordinary quantum field theory, as lambda tends to 0, how do you get log lambda?
So you have to, this formula, if I understand correctly, comes from resumming an infinite number of diagrams. Because you can show that they all contribute at the same order. And that's where you get the 1 over
So
lambda
resumming is going
and the log lambda, yeah.
Can you tell us more about the viscosity of non-relativistic theories? I mean, you said that there is no C constant, so it seems as if it's relativistic or non-relativistic doesn't matter. Yeah.
Good point. But yes, so this, first of all, this bound here is a conjecture, and then you can think about to what type of systems, if any, you would expect this bound to apply. In my opinion, it's not. You should not expect it to apply to non-relativistic systems, because in a non-relativistic system, you can actually increase the entropy density without changing the viscosity. For example, by increasing the number of species. And so you can always, in principle, drive this ratio down. So I don't expect there to be a lower bound. If you try to do that with a theory that's relativistic, that you force the theory to have a relativistic completion, then that's much harder. So even though...
Take 3 copies of n equals 4 super Young mills. Don't I get 1 over 12 back? Completely non-interacting.
I'm not sure. You mean taking the gauge group to be a product, for example? I don't think actually that's going to change the ratio, because you could do this calculation for theories that have a product gauge group.
If they're with gravity, they certainly have interactions. And just non-interacting systems, entropy is additive and viscosity stays.
I'm not sure. Let me think about it. Any more questions?
Just a clarification. So, when you mentioned the 1 over lambda 3 halves, you were talking within n equals 4 super Young mills. So, has this has also been done for all the other theories?
No. This correction, no. The leading result has been checked for pretty much every theory we have a gravity dual for. But this is very hard to compute, the correction. And this has only been done for n equals 4.
Are all the alpha prime corrections known for n equals 4 that are necessary to compute that coefficient?
That's a good question. I can tell you my opinion in private.
That's a no then.
It's very subtle. It's very subtle. Honestly, I'm not an expert on that, but you have to be very careful. So I actually don't know. Any more questions?
This 1 over lambda correction, it was computed from the supergravity side.
Yes, exactly. This is a correction to the infinite coupling result.
What, r to the 4th?
Yes, it's an r to the 4th correction, which when reduced to 5 dimensions is an r squared correction.
What are the fields done here in this solution?
Here, the only thing you have is the metric. The dilaton is still constant, and the phi 4 is still given by the same expression as at 0 temperature. Yeah.
One other point, David, if you put h bar to 0, then of course you just get the result that the eta has to be positive.
Mm-hmm.
So the bound itself, the lower bound, that's obviously some quantum effect. And the question is, is there any intuition about how quantum mechanics?
Yeah, you can actually argue.
Forces effectively, I mean, the bound would be eta greater than 0, so you could be as small as possible. So quantum mechanics must force it to be positive, non-zero.
Yes, so you can argue for the fact that eta over s is bounded from below. You don't know the coefficient, but for the fact that there is a lower bound by using the uncertainty principle.
Yeah, that's what I imagine. How does that work?
You just put bounds on the entropy density, the mean free path of your particles, etc., because the viscosity is related to the mean free path, the interaction, cross section, etc., etc. It's really just a back of the envelope calculation, and you get that eta over s has to be of order 1 in h bar units, but of course you don't know the coefficient. So in some sense, what this is giving you is a model in which you can calculate explicitly that coefficient, and it turns out to be universal. It's always 1 over 4 pi. Any more questions? Okay, in that case, let me now discuss the connection between what I just said and QCD, or the quark-gluon plasma in particular. So, yeah, how do I lower this computer? Okay. So as I told you, at a temperature of about 175 MeVs, QCD undergoes a crossover to a new phase. And if you look, yeah, here it is. So this plot is a plot of the energy density in units of T to the fourth for QCD for different numbers of flavors as a function of the dimensionless temperature T over the critical temperature or the deconfinement temperature. And what you see is that there is a very, very rapid crossover in which the energy density, for example, increases very quickly, and then just above the deconfinement temperature, immediately just above, it stabilizes at a value that's equal to about 80% of the value for a free gas of quarks and gluons. Okay, so if you take the field content of QCD and assume there are no interactions between the quarks and gluons, you get some result that's denoted here, the Stefan-Boltzmann result for the free theory. And that would be, for example, for this curve would be up here, for this one up here, and so on. And in all cases, the result that you get from the lattice just above the confinement is about 80% of the free result. Okay? Now, this fact was interpreted, the fact that there is only an 20% difference between the free result and the lattice, was interpreted by part of the community as meaning that the quark-gluon plasma in QCD is weakly coupled immediately above the confinement, or just above. Because after all, interactions account for only a 20% difference between the energy density in the free theory and in the real result, if you believe the lattice result. That was a very widespread belief. Okay? If that were, yes?
What's the difference between 2 plus 1 and 3 flavors?
2 plus 1 means 2 light ones, 1 heavy one. So if you believe that statement, that the quark-gluon plasma is weakly coupled, then you would expect that for the quark-gluon plasma, the ratio of eta over S should be very large. Because remember, I told you at weak coupling, you can actually calculate it in perturbation theory, and you get something that's very large. It goes like 1 over lambda squared. Okay? That was the state of mind in the community until Rick turned on. Now, before I tell you what Rick found, let me make a number of comments. First of all, I think this interpretation is very counterintuitive, I think. Why? Well, first of all, if you look at other thermodynamic quantities, like the pressure, you see that they don't increase so quickly, but instead they do so gradually over a range that goes between TD confinement and at least 4 times TD confinement. Okay? So the behavior on which that belief was based only applies to the energy density, essentially. But it's not true for other quantities. Secondly, and I think more conceptually, I don't see any good reason for why a theory that's sufficiently strongly coupled to confine to become immediately very weakly coupled just above the confinement. Of course, in QCD you know that at very high temperatures, asymptotically high temperatures, because of asymptotic freedom, the coupling is going to become weak, and the quark-gluon plasma will behave like an almost free system. But there's no reason in principle to expect that to extend all the way down just above the deconfinement temperature. And finally, we saw before that the fact that some thermodynamic quantity is very close to the free result doesn't mean you're at weak coupling. Remember, for n equals 4 super Young Mills, the entropy at infinite coupling is a factor of 3/4, which is 75% of the entropy at zero coupling. So if I tell you what the entropy is, there's no way you can use that to decide if you're at weak or strong coupling. And in fact, you will realize that 75% is much closer to 80%, or let me put it differently, 80% is closer to 75% than to 1. And so this result, in hindsight, you could say, if you were very perverse, that should have been interpreted, the energy density, as indicating that the quark-gluon plasma is very strongly coupled. So in any case, we want to know what happens for QCD, okay? What is the ratio of eta over S for QCD? If you believe this interpretation, it would be very large.
Excuse me, can you tell us something about QCD and conformal symmetry about the deconfinement?
Say that again. Sorry, I can't hear you.
QCD and conformal symmetry above deconfinement.
If I can say something about that?
Yeah, yeah.
Well, I can say that...
Because n equals 4 is conformal, yeah? And if you try to compare any results from n equals 4 to QCD, you have to take into account this conformal symmetry.
No, so n equals 4 at finite temperature is not conformal.
It's not.
Because you have a scale.
Yeah.
Now...
But if you demand lack of bulk viscosity in edge-momentum tensor, then you mean that its trace is zero, like in conformal theory.
What you mean is the theory is conformal at zero temperature. That's the correct statement.
Sure.
With temperature, there's a scale, and so physics depends on what energy you're probing compared to that scale. So it's not scale invariant. Now, some people...
It still implies things about the finite temperature theory.
I agree. I agree. Conformal invariance at zero temperature has consequences. For example, that at finite temperature, the only scale is the temperature. Okay? But it's not conformal. Nevertheless, some people interpret this result here as suggesting that there is some sort of effective or some conformal invariance, at least in this restricted regime between TD confinement and 4 times TD confinement, approximately. But I don't know of any way of making that precise.
And what about the running of the coupling in case of n equals 4 in finite temperature? Because, you know, usually it's said that the theory is conformal and the beta function vanishes and the coupling is really constant. But if you have a finite temperature, you have this conformal symmetry broken by the scale. It's quite obvious. And what about the coupling constant?
But it's broken classically because you're introducing you're looking at a state in the theory, a thermal state that breaks that symmetry, but the theory is still a conformal theory. I think there's a lot of semantics here. I don't know if I answered your question, but okay, let's discuss it at the end then, if that's okay. Because I think for example, when people say that this suggests some conformal symmetry, those are words, but I don't know how to make that precise, and I'm not aware of a compelling way of making that precise. And in fact, as I said, if you look at other thermodynamic quantities, they don't display the same behavior. So this is one suggestion. The other suggestion is to look at ADS-CFT. And as I told you, in all the theories at strong coupling, for which we know how to calculate it holographically, the ratio is 1 over 4 pi. And because it's so universal, you could actually, if you're very optimistic, you could say that all non-abelian plasmas look alike, meaning, as far as this ratio is concerned, meaning that it's a property of just being at strong coupling and perhaps large n, but it doesn't depend on the detailed field content of the theory, whether or not you have fundamental matter or chemical potentials, etc. So if you believe that, and if you think that QCD just above the confinement is going to be strongly coupled or reasonably strongly coupled, if you believe that, all of that, then that suggests a prediction, which is that eta over S for QCD above the confinement should be close to 1 over 4 pi. Maybe not exactly 1 over 4 pi, because of course you're not at infinite coupling, you're not at infinite n, etc., and it's not n equals 4. but it should be close, as opposed to very large, as you would get in perturbation theory. Okay?
Close meaning a factor of 2 or 10 or...
I mean something, of course easy to say in hindsight, but something, let's say, between 1/4 and 4 times 1/4 pi. But not a factor of 100.
Maybe
Yes.
you just reminded us that at very high temperature, it should look more and more free.
Yeah.
You told us earlier that for free gas, the ratio of E to RS will grow very, very, very large.
Yes.
So for QCD, perhaps with distinction to n equals 4, should one not expect then that that ratio add back to become larger and larger the higher the temperature?
Yeah.
Maybe it does
Yes.
in the experiments.
Yes.
But on the other hand, for n equals 4, you don't have that.
That's correct.
You don't have that same intuition doesn't apply.
That's correct. Thank you. So that actually is addressing one of the things that I wanted to say, which is that the goal here is to use n equals 4 at strong coupling to model QCD in some regime around around the deconfinement temperature. But of course, if you go to 100 times the deconfinement temperature, you're going to be at weak coupling, and things you derive using holographic duals at very strong coupling have less of a chance to apply.
On the other hand, in QCD, the other scale is the deconfinement scale. So
Yes.
in order to have a theory that really only has one scale, you have to be far above the deconfinement.
Well, that's not clear. That's not clear, because in some sense, so in principle that's true, but you have to quantify it. And for some purposes, QCD above the confinement quickly forgets about this dynamically generated scale, the confinement scale, and just behaves like a real plasma, where the only relevant scale is the temperature. But of course, as you're saying, that limits the range on both sides that you have a hope of getting a hand on. Absolutely. Yes.
So you've got this NF over NC
Yeah.
expansion, and
Yeah.
this parameter is 1
For QCD. Yes.
So why should you expect to trust anything? Maybe you've got an uncontrolled expansion in something which is order 1. Why should...
Well, there's a previous question you could ask me, which is why something I derived in the large n limit, be it with or without fundamental matter, it doesn't matter because we're in the large n limit, has a hope of applying to QCD with 3 colors.
I'll ask that as well.
Okay. So the answer to that is that you don't know a priori. In QCD, the large n expansion works very well for some observables and not very well for others. And of course, whenever you have a Taylor expansion, you don't have enough with knowing what the expansion parameter is. You have to know what the coefficients are, because otherwise you can't really say whether it's a good approximation to truncate at a given, say, at large n. So you don't know a priori. That's the answer. What I'm saying is that for all the theories for which you can calculate reliably this ratio, okay, and admittedly they are in the large n and at strong coupling, for all those theories, you always get the same result. And I'm saying if you're very optimistic and you think that the 1/n expansion is a good approximation to QCD, at least for this observable, as it is for some others, but not for all, then you may be willing to accept a suggestion that this ratio should also be small for QCD. Does that answer your question? But it's not guaranteed.
Now, what is the measured ratio, eta over S from Rick, and how large are they?
I'll get to that. Before I do that, any other questions? Good. So in case that not everybody knows, what they do at RIC is to take heavy ions and collide them. So this is a movie that somebody took of what it looks like. I don't know if you can see that, but these are 2 Lorentz contracted, because of the motion, ions that collide. Most of them, unless it's a central collision, fly by. But what's left behind is something that gets really hot because of all the kinetic energy. And it gets hot enough so the temperature, first of all, there's evidence that this thing thermalizes. It reaches thermal equilibrium very fast. And secondly, that the temperature at least the initial temperature, is between 1 and 2 times the deconfinement temperature. So what you're creating is a fireball of deconfined quark-gluon plasma. Okay? Now, not only there is evidence for thermal equilibration, but there is also evidence for strong coupling dynamics. For example, if you look at back-to-back jets, if you have in the initial collision, you have partons, very energetic partons colliding with each other. Okay, so those will give rise to jets that move in opposite directions. If those jets or those moving partons didn't interact strongly with the plasma, what you would get when you look at these back-to-back jets for heavy ion collisions and for proton-proton collisions would be the same. Because the only difference between the two is that in one of them you have this medium in which this back-to-back jet is propagating, and in the other one you don't. And what you see is a very strong suppression of back-to-back jets. And the reason for that, or the potential explanation for that, is that if you have, say, 2 partons or 2 jets produced near the surface of this fireball, one of them will of course escape more or less undisturbed, but the other one has to propagate through a medium. And so if the interactions with the medium are very strong, then what you will get here is strongly suppressed, as compared to collisions of, say, proton-proton collisions. Okay? So that's part of the evidence that suggests that the coupling is strong. And finally, once you accept that this is a strongly coupled system which has reached thermal equilibrium, then you can try to describe it using hydrodynamics. That's very hard because hydrodynamic simulations are very hard, in particular in 3+1 dimensions. Okay? And also in particular, just a second, including the effect of shear viscosity. But to whatever extent those simulations have been done, the number so what people do is they run these hydrodynamic simulations where eta over s is a parameter. And then they tune eta over s to the value that best fits the data when you plug it into the simulation. And the number they get for that ratio is something in between 1/2 and 4 times 1/4 pi. So you see that it's reasonably close. In fact, it is the closest that any substance that's been ever measured in nature comes to 1/4 pi. Any other substance has a ratio that's greater than even 4 times 1/4 pi. For example, remember liquid helium is 9 times 1/4 pi. So at RIG they have these cups that say that RIG serves the perfect fluid because it's the fluid in nature that's been measured with the lowest ratio of viscosity to entropy density. Any perturbative calculation that has a chance of applying, being extrapolated to some plausible value of the coupling at RIG gives a ratio that's at least 10 times 1/4 pi. So in this sense, with all the caveats and all the reservations you should have, if you want to be very bold and provocative, and some people have done this, you could say that the best calculation for this ratio at RIG is a string theory calculation. Okay, if you say this, some people will actually get you in trouble. Any questions?
What's the evidence we reach thermal equilibrium?
The evidence. For example, the fact that hydrodynamics works so well. So hydrodynamics assumes local thermal equilibrium, and it never worked for other collisions. For example, a heavy ion and a proton. It doesn't work for those because that thing doesn't reach thermal equilibrium, so it's not a big.
Work means what? What are you measuring when?
So what you do is, using hydrodynamics, you use central collisions to fit some parameters, like for example the initial temperature or some coefficients you don't know that you have to determine experimentally. And with that input, you predict, using hydrodynamics, the particle abundances that get produced and also the angular distribution for non-central collisions, for example. So the evidence part of the evidence comes from the fact that hydrodynamics works very well.
I'm a bit confused because hydrodynamics is a liquid with very few parameters, and there's not much it can do. It can't produce many particles if you're just in a hydro description. All it can do is slosh around and expand a little bit.
Yeah, but when it expands, it cools down, and when it cools down, eventually it hadronizes. Okay, so you need not only hydrodynamics, but some model for how this thing hadronizes.
It must be just the shape that this ball of fluid takes during
No,
where it hadronizes. Is that the information?
there are lots of parameters. There's the local entropy density, local temperature, local velocities, etc., etc. So, in a sense, you're right. Yes, it's a liquid. So you have a finite number of parameters that you need, but you still need some information, some input to determine some of those, and about the initial state as well.
So it's not in thermal equilibrium in the sense there are temperature gradients in this thing?
It's local thermal equilibrium. Local thermal equilibrium. Yeah. And indeed, there are, for example, pressure gradients that give you this elliptic flow, because the gradient is greater in one direction than the other. So this is the best way to build a bomb if you want. You don't want a spherical explosive.
We just mentioned this about this elliptic flow. So my understanding of this this hydrodynamic approximation is you assume the system sort of comes into local thermal equilibrium, and then you just fit just the elliptic flow to the hydrodynamic description. So you're just fitting one parameter, which is the sort of evolution of the central collision, sort of this elliptic region in the transverse plane. Is that right, or is there more to the fit?
You mean
eta or s?
You mean whether there are more predictions than that one? Oh yeah. You can predict. For example, you can predict the elliptic flow for different species of particles. You can predict the relative abundances of how many pions versus how many kaons, say, are produced, etc., etc. So.
But that's not part of hydrodynamics, right? That requires some knowledge of how hydrodynamics eventually moves into the hydronization.
Yeah. As I said, you need not only hydrodynamics but a model for chemical freeze-out and hadronization and everything else. That's why it's so complicated, and you should take these numbers with a lot of caution. This may change. But from amongst the people I speak to, they seem quite convinced that they don't know what it is, but it's certainly small. And definitely small enough to rule out any perturbative explanation. That's the main message I want to convey. I also want to emphasize that it could be smaller than 1/4 pi. I have no problem with that. It could be. What's important is that it's close to 1/4 pi.
Okay, but then let me go back to the previous conjecture about the bound.
About the bound, yeah.
About the bound. So if it is less than 1/4 pi, then you certainly have a relativistic quantum theory which violates the bound.
Yeah. But that bound, I don't have any stake invested in that bound. It seems it's certainly saturated by all the examples we have, but those are examples at infinite coupling and infinite n. So 1/n corrections, 2 coupling corrections, everything could lower it.
There's no real evidence for that bound at all, right? Just optimistic projection.
Well,
for example, if I came and gave you a quantum field theory tomorrow that beats this bound, you wouldn't have to look for a loophole in the argument.
Exactly, but nobody has done that. Nobody has done that.
Okay, so it's just the fact that we can't calculate a strong coupling other than in gravity theories, which is...
It could be. It could be. Yeah.
Are we finished?
Yes, we're sorry. I think.
I guess we had the question session. If there's any more questions, then now's the time to ask.
So do you actually get the same bound in integral over S for 3-dimensional gravity?
Sorry?
You get the same bound of 1/4 pi from 3-dimensional gravity?
3-dimensional gravity.
You mean
Yeah, I think you'll get this.
No, the answer is no. There is no shear viscosity.
No, if you're in, oh, sorry, three-dimensional, I'm sorry. No, three-dimensional gravity would be dual to a 1 + 1 dimensional theory. You need two spatial directions to define viscosity. Yeah.
Then a second one, I understood that if you include like higher derivative corrections to the gravity theory, then you would generically violate this bound, right? Is that correct?
No, the only higher derivative correction that's been calculated raises the value above the bound.
Yeah, violated, that's what I mean, like it will not saturate it.
It will not saturate, yeah, it doesn't violate it.
So just assuming the bound were to hold, and that's kind of saying something non-trivial about like all high derivative corrections in kind of all gravity theories. So what would that profound thing be?
Well,
or any idea?
first of all, I'm not sure it would be that profound, because it's just saying something about the sign of the correction.
That sounds profound enough.
Okay, well, profound is a subjective concept, but in my opinion, well, okay, whether it's profound or not would depend on how exactly that statement gets rephrased in terms of the gravitational effective action for string theory in these backgrounds. But yeah, I don't have much to say about that.
Oh, yes, maybe one more. So it's at least conjectured that in neutron stars there can also be coagulant plasma layers, something like this. Do the astrophysicists have anything to say on this eta over S?
The point, thank you for the question. I will come to this hopefully at some point, maybe in the last lecture. But neutron stars may have a deconfined QCD plasma, but that's at very, well, reasonably large chemical potential. So if you look at the phase diagram for QCDs, you plot temperature and baryon number chemical potential. RIC, so there's this crossover over here, and then there is supposed to be a critical point and a line of first order phase transitions, and RIC is somewhere over here. Neutron stars are somewhere over here. So it's a completely different regime. It's a very cold but dense QCD phase. And nobody really knows what the core of a neutron star could be like. I mean, and the phases of QCD here keep, the number of phases keeps increasing, and it's a very complicated phase diagram. So
Time dependent.
yeah, but it could certainly be. I mean, that's one of the directions that hopefully I'll have time to talk about, because it's very interesting, because the lattice at finite chemical potential is even harder. So anything you can say, I think, may be useful.
Okay, let's thank David again.